All right, we're going to continue with some more log problems here, but now we are solving for kind of other aspects, maybe the base, maybe what's inside of the log. And so on all of these, we're just going to switch it to exponential form and then evaluate. So that's our first step. So this time it's already set up as an equation here. So on number 12, I'm going to switch it to exponential form. So we'll say the base is 5. The new partner is going to be 4. And then that's going to equal x. And so you can multiply that out. Whenever I do these fourth powers, I really just do 5 squared times 5 squared. So I know that 25 times 25 is 625. All right, next up here, number 13. Now this one, we got to remember that when it's no base written, it is always an invisible base 10 if it's a log. As in ln, if there's no base written, which there never will be, it'll always be e. But for a log, it's base 10. So then I will write it as a 10 to the power of 3 equals x. And so the 10 to whatever power is just a 1 with that many zeros, so I know that that one's 1,000. Okay, next up here we'll do number 14. So here our variable is in the base, so I'll say now that base will be x to the power of 2 equals 64. We'll square root both sides here. Now usually when we square root we would say x equals plus or minus 8. However, there is kind of a rule on logarithms here, especially kind of at this level of math, the base is always going to be greater than 0. And so I'm going to say here that x is going to equal 8. All right, now number 15 here, we'll say x to the 4th power equals 81. And for this one, we will do the 4th root. You can also do the 1/4 power if you want to look at it like that. And technically on a 4th root, on any even root, we should still do a plus or minus here. So I'll go plus or minus. And then the 4th root of 81 is 3. Because 3 times 3 times 3 times 3 is going to give you 81. However, once again, with that same rule, we're just going to only look at the positive answer there because the base of a log and the base of an exponential equation is going to be positive. All right, next up here, we're going to start talking about domain a little bit for logarithms. And so really quick before we do that, I wanted to remind you that we always did have, before we do that, I lost this line of text here on the copy, so if you can add that in, the inside of a log cannot be a blank number or 0. We'll get to that in a minute. Before we do though, I wanted to remind you we we had 2 rules for domain, and I think I mentioned that we'll do a third one later, and later has arrived, and so now we're going to learn this third rule. So quick refresher though on our first 2 rules. The first rule we said was a denominator cannot equal 0, so it's a very important rule for domain. The next rule of domain we learned was the inside of an even radical, so a square root or 4th root, must be greater than or equal to 0. And now the last rule we're going to learn today is the inside of a log cannot be a negative number nor 0. So to find the domain of the log, take the inside of the log and set it greater than 0. So there's the key right there, the inside of the log greater than 0. Now some of you may be wondering why is that. So if you think about it here, let's do a log. Let's say it's base 2 just to make it easy, but it doesn't really matter. And let's say, what if I said log base 2 of, let's say, negative 4? Why am I not allowed to have a negative in there? Well, let's say that's equal to x. And then we would say 2 to the x power equals negative 4, right? Well, is there an exponent that will turn that x into negative 4? The answer is no, because if you think about this negative 2 power, that's not negative 4. That would be 1 over 4. So it's not possible, and therefore we're not allowed to have those negatives inside of the log. Now, when you get to much higher levels of math, you can actually do this with imaginary numbers, but for the purposes of domain, we're going to say that is not allowed. Furthermore, if we said log base 2 of 0 equals x, we'd be saying 2 to the x power gives me 0, and that's not possible either. Once again, you might think that that's 0 right there, but 2 to the 0 power is actually 1. It's not 0. So this is why we have this rule that the inside of the log must be greater than 0. So let's get to our practice problems here. So number 16. We have the inside of a log here, and so to find the domain, if the question is domain, we just take the inside of the log and set it greater than 0. and we solve, so x would be greater than 4. And we're going to want this in interval notation, so I'm going to say that's from 4 to infinity. Next one here, we have the inside of a log here, so I'm going to say 8 minus 2x is greater than 0. Now, whenever I see a negative in front of an x on these inequalities, I already am thinking I'm going to have to flip the inequality at some point on this problem. So I'm just going to subtract the 8 over. Say negative 2x is greater than negative 8. I'll divide that by negative 2, which means I have to say x is less than positive 4. So that's going to be from negative infinity to 4. And then lastly here, we have a natural log. Now remember, the L in ln does stand for log, and so even though this is an ln, we still follow the same rule. The inside of a log must be greater than 0. So for the purposes of domain, the base doesn't really matter. You can see I did a base 2, I did a base 5, and then lastly I did a base e. But for the domain, all we're really worried about is what's inside, and that must be greater than 0. All right, now this one is actually a little bit more intense because we have the nonlinear inequality right here, which means we have to use the, remember we have to use, when it's like a squared with a greater than, we have to use the test points. And so I'm going to be doing that on this problem here. I'll write that a little neater. Okay, so I'm going to factor it. 3 minus x, 3 plus x is greater than 0. We're going to go to the number line here. I got negative 3, I got positive 3 with open circles. And then I'll test out x equals negative 4. And that actually makes the first one, 3 minus negative 4 is positive. 3 plus negative 4 is negative, so that's negative. For x equals 0, I think they would both be positive. Yep, 3 minus 0, 3 plus 0. That's good. X equals 4. It's going to be 3 minus 4 is actually negative now, and then the other one is positive, so that's a negative. So we're in between here, so I got from negative 3 to 3. All right, next up here, we're going to get into graphing logarithms. And so to graph logarithms, how I graph logarithms, and this isn't the only way to do this, but the way I think of it is logarithms are the inverse of exponentials. So that's a very important concept to understand. And so if we remember that logarithms are the inverses of exponentials, it's going to be a lot easier to graph these. So let's recall how we graphed exponentials. So for exponentials, we had our points. We had 0, 1. We had 1, base. And then we had a horizontal asymptote at y equals 0. So for logs, which we'll do over here, remember that the inverse means that we switch x and y. And so our points are going to be, instead of 0, 1, since it's the inverse, we'll do 1, 0. And then instead of 1, base, since this is the inverse, we're going to do base, 1. And then instead of a horizontal asymptote, we are going to do a vertical asymptote. And a vertical asymptote is going to be defined as x equals 0. So we are then going to still do our transformations. So for our transformations, inside the log is going to be left or right. And that's going to be x lies, like always. And then outside is going to be affect the up and down, so it's going to be the up and down, okay? All right, so let's get started here on number 18. So for number 18, we're going to start off with our points here. So we have 1, 0. We have base, 1. Now our base here is 2. And we're going to start off with a vertical asymptote at x equals 0. So now we'll check out our transformations here. I have an x plus 3 inside the log, and so that means I'm going to go x minus 3 here. Once again, that's just x lies. And then I also have a negative out front, so the negative on the outside is going to affect y, so I'm going to turn my y's negative. Notice that the base 2 is not a transformation. The base 2 is taken into account when we do our base, 1, but it is not a transformation. So I'm going to subtract 3 from my x's. I'm going to make my y's negative. So 1 minus 3 will be negative 2. There's no such thing as negative 0, so I'll keep it like that. 2 minus 3 is negative 1, and then there is a negative 1, so I'll put that there. And then my vertical asymptote, now that it's vertical and it's x equals a number, that's going to be affected by my x transformation, so that is going to point to x equals negative 3. So I'm going to draw my vertical asymptote at x equals negative 3. And I'll graph my 2 points here, negative 2 comma 0, negative 1 comma negative 1. Now, remember the asymptote. The graph will approach the asymptote, and it's just like our exponentials, it's going to be one-sided, so it's either going to be going up or down as it gets closer to the asymptote. And so in this case, it's going to be going up because that point is a little bit closer to the asymptote. And on this one, it's going to go away. Now, what this graph actually is, if you kind of tilt your head sideways, I normally do this with my paper in the classroom, but since we're doing this online, tilt your head to the side. You should see an exponential function there on its side. So if you tilt your head, it looks more like a horizontal asymptote and an exponential growth function. So now this is our logarithmic function. Now we didn't mention domain here, so let's go ahead and evaluate that now, and we'll see how that affects, and we can kind of see that on the graph. So for the domain on this one, we know we take the inside of the log and set it greater than 0. So we'd say x is greater than negative 3. And so that's going to give us an interval notation of negative 3 to infinity. And I think you can really see that interval of negative 3 to infinity because you can see here the graph does start at negative 3. Now it doesn't actually start there because it's an asymptote. Remember, this never actually gets to negative 3. That's why there's a parentheses here, because there's not an actual point at negative 3. It starts just to the right of negative 3 and then goes all the way to infinity. If you're wondering about range on this one, all log functions have a range of negative infinity to infinity. This goes up forever, and this does go down forever. Now it's going right a lot faster than it's going down, but it would never stop going down. All right, next up here, we'll do number 19. So for this one, we're going to start off with our same points. So we'll go 1, comma 0, base, comma 1. Now our base is 1. And we're going to have a vertical asymptote, which will be at x equals 0 to start. Now we're going to do our transformations here. So our transformation, we actually only have one here, and it is y minus 2. Our x is not going to stay the same. Now some of you may be thinking, hey, it's x minus 2 inside the log, but for adding or subtracting, if adding or subtracting is not in parentheses, then it's assumed that it's outside. So this minus 2 is not in parentheses. That means that it's outside and affecting y. If they want it inside, they have to use parentheses for adding and subtracting. Multiplying, you technically don't need to use parentheses, but for adding and subtracting, you do. Okay, so let's apply our transformations here. So we're going to get that, obviously our x values are going to stay the same, and that'll actually mean our vertical asymptote is not moving. Our y values are going to get shifted down too. So there you go on that. So let's draw our vertical asymptote here, imaginary line. And 1, comma negative 2. And then 3, comma negative 1. Be right there. And so there we go. All right, next up, let's check the domain again. You could probably do it from the graph now, but if you were to do it according to our rule, we would take the inside of the log, which in this case is just x. Remember I said that minus 2 is not inside the log unless it's in parentheses. And we have to solve it, which is already done. So this domain would be from 0 to infinity, which once again, I think you can really see on this graph because it starts at 0 without actually ever getting there, and then it goes all the way to infinity. All right, next up, number 20. So this one probably be the trickiest one for a couple reasons. First of all, it's an ln, and so remember for ln, that's really a base e. Now remember when we graph these for exponentials, I always said for graphing e, you can always just use 2.7 is fine. It's kind of close enough for graphing. I wouldn't want to use it for any calculations, especially with money. But for graphing, you can just go ahead and use 2.7. Honestly, if you use 2.6 or 2.8, nobody would know the difference. So just a general idea. It doesn't have to be perfect on that one. So that's the first thing. So not a huge deal there. I think we can power through it. The next thing we have to look at is our transformations. Now we have a negative inside, and that's going to make our x's negative. I know x lies, but that's really just for the adding or subtracting. When we have a negative in there, it's just going to flip it across the y-axis, so we can do that easily by just making our x's negative. We have two transformations to y, which is going to be multiply it by 3 and then subtract 2. And that's for the two numbers, the multiplier out front and then the subtracting 2 out back. Okay, so let's apply our transformations here. So this is going to become -1. This is going to become -2.7, so that wasn't too hard. For the 3y minus 2, so I'm going to go 3 times 0 minus 2 will be -2. And then 3 times 1 minus 2 is going to be +1. So that wasn't too hard either. Our vertical asymptote gets the x transformation, but there's no -0, so it's going to stay at 0. All right, so now we'll draw our vertical asymptote at 0. And then we got our points, so -1, -2 will be there. -2.7, 1, that'll be about there. And I know that's not perfect, but like I said, don't stress about it. With the decimals there, we're just getting a ballpark what this generally looks like. And so there we go. Okay. Approaching the asymptote as it goes down in this case, because that point was closer to the asymptote, and then running away from the asymptote on the other side. Now, very important aspect of this one I wanted to talk about was the domain. So let's talk about that now. And so the domain on this one, I have to take the inside of the log, which in this case is a natural log, but it's still a log, and set it greater than 0. So in this case, we have a -x inside the log. So I'm going to say -x is greater than 0. So I have to divide by -1 to get rid of that, which means I have to flip the sign. Obviously, it's not going to affect 0, but it is going to affect the inequality. So it's going to become x is less than 0, which would give us an interval notation of -infinity to 0. And I think you can really see this on the graph, because instead of starting at 0 on this one, it's actually starting way over here and then stopping at 0. Once again, that's a parentheses around the 0 because it doesn't actually get to that asymptote, obviously. But it does stop just to the left of 0. So you can see on all of these that the asymptote is very much connected to what's going on with the domain. So the asymptote keeps the graph on one side or the other, and that's going to affect the x values we're allowed to plug in, and so that's obviously what the domain is. So I guess if you wanted to say something, you could say that the domain is just all about that asymptote. All right, that's it for today's lesson. I'll see you guys later. Bye.